Hello learners. Let's start with something you see almost every day: spectacles, cameras, or even a magnifying glass. What do they all have in common? Yes, they use lenses. A lens is simply a transparent piece of glass or plastic that bends light, or in physics terms, refracts it. Depending on the shape, we have convex lenses, which are converging lenses, and concave lenses, which are diverging. Convex lenses have positive focal length, while concave lenses have negative focal length. By placing objects at different positions, these lenses can form real or virtual images, magnified or diminished. And that's exactly why lenses have so many applications in our daily life, from cameras to projectors to microscopes. Now imagine trying to capture a photo with your mobile camera. What ensures that the image of your friend forms sharply on the sensor? A convex lens inside your camera. Convex lenses are masters at focusing. When we keep an object between focus f and twice the focus, 2f, the image formed is real, inverted, and magnified, perfect for cameras and projectors. Mathematically, this is explained by the lens formula: 1 divided by f equals 1 divided by v minus 1 divided by u. Here f is the focal length, v is the image distance, and u is the object distance. That same principle allows projectors to magnify a tiny slide into a huge picture on the screen, and microscopes to enlarge the tiny world of cells. Convex lenses magnify, but concave lenses? They spread light apart. Imagine looking through a door peephole. The tiny glass is actually a concave lens that gives you a wider view. In physics terms, concave lenses take parallel light rays and make them diverge, as if they were coming from a virtual focus. The focal length here is negative. These lenses are crucial in spectacles for myopia or short-sightedness because they help spread out incoming light so the eye lens can focus it properly. In cameras too, concave lenses are combined with convex lenses to correct optical defects and sharpen images. Imagine being able to see the world around you in vivid detail, adjusting effortlessly between objects up close and far away. That's all thanks to the lens in your eye, a perfect example of physics in action. The crystalline lens in your eye is a convex lens, and just like a camera lens, it helps you focus on objects at different distances with the help of ciliary muscles that adjust its focal length. As light passes through the lens, it focuses on the retina, where the image is sharp, real, and inverted, much like a camera capturing an inverted image on film. For normal vision, your eye constantly shifts focus between near objects, like when reading, and distant objects, like watching a sunset, by adjusting the lens shape. Not everyone has perfect vision though. For people with myopia, nearsightedness, the focus point falls in front of the retina, and concave lenses are used to correct it. In contrast, for hypermetropia, farsightedness, the focus point falls behind the retina, and convex lenses are used for correction. Interestingly, the eye is the most natural example of a lens application, working all the time without you thinking about it. The magnification formula is magnification equals image distance divided by object distance, or m equals v divided by u, where v is the image distance and u is the object distance. The closer an object gets to your eye, the more it gets magnified. So, your eye is a complex yet elegant system that works tirelessly to let you see the world clearly, all without you even noticing. Isn't that amazing? See you next time for more fascinating physics. Now let's travel from the smallest cells to the farthest stars. Both microscopes and telescopes use combinations of convex lenses. A telescope uses a large objective convex lens to collect light from distant stars and form a real inverted image. This image is then magnified by a smaller eyepiece lens. The magnifying power of a telescope is given by the formula Capital M equals focal length of the objective divided by focal length of the eyepiece. On the other hand, a compound microscope uses a short focal length objective lens to form an enlarged real image, and then the eyepiece magnifies it further. Its magnifying power is given by capital M equals V divided by U multiplied by D divided by FE, where V and U are image and object distances, D is the least distance of distinct vision, and FE is the focal length of the eyepiece. So whether you are looking at a tiny bacterium or the rings of Saturn, lenses make it possible. Hello, physics enthusiasts! Today, we are diving into the world of lenses, specifically looking at a convex lens. You know, those lenses that focus light and create magnified images, just like in eyeglasses or cameras. So here's the scenario. You've got a convex lens with a focal length of 10 centimeters and an object placed at a distance of 15 centimeters from the lens. Our task: to find the image distance and a magnification. Step 1. Lens formula. We start by using the lens formula, which is pretty straightforward. 1 divided by the focal length equals 1 divided by the image distance minus 1 divided by the object distance, where the focal length is represented by f, the image distance is represented by v, the object distance is represented by u. So, we substitute our given values into the formula. Notice that the object distance u is negative as per the sign convention in optics. Step 2. Substitution. Now, let's substitute the values. 1 divided by 10 equals 1 divided by v minus 1 divided by negative 15. This is a simple substitution step where we insert f equals 10 centimeters and u equals negative 15 centimeters. Step 3. Solve. We can now solve for v, the image distance. Rearranging the equation, 1 divided by v equals 1 divided by 10 plus 1 divided by 15. Solving this, we get v equals 6 centimeters. So, the image is located 6 centimeters from the lens. Step 4. Magnification. Now, let's find the magnification using the magnification formula. Magnification equals v divided by u. Substitute the values we have. Magnification equals 6 divided by negative 15, which equals negative 0.4. The negative sign tells us the image is inverted, and the magnitude of 0.4 means the image is smaller than the object. Quick insight. One thing to remember while doing these lens problems is the sign convention. The distances and focal lengths follow certain rules: negative for objects on the left of the lens, positive for objects on the right. Keep that in mind, and you'll breeze through lens problems in no time. And there you have it. We calculated the image distance and magnification using the lens formula. Always remember, these formulas are not just numbers, they represent real-world phenomena we see every day, from magnifying glasses to cameras. Keep practicing, and in no time, you'll be able to tackle any lens problem thrown your way. See you in the next session. So let's tie it all together. Convex lenses power cameras, microscopes, telescopes, and even our eyes. Concave lenses help in vision correction and wide-angle viewing. The lens formula, 1 divided by f equals 1 divided by v minus 1 divided by u, is our guiding tool to calculate where images form. And magnification tells us whether the image grows larger or smaller. The story of lenses is really the story of how humanity extended its vision into the tiny invisible world and across the distant galaxies. I hope this gives you a clear and confident picture of applications of lenses. Until next time, keep observing the world through the lens of physics.